In this video, we are going to continue to talk about the reactions involving amines. We are first going to be reviewing the synthesis strategies discussed previously. Overall, you should know that there are three options if you want to produce a primary amine. The first option is that you have potassium thalamide, thalamide, sorry, is potassium thalamide that through Gabriel synthesis you can have an alkyl halide alkylate the nitrogen atom, then hydrazine will create that primary amine. Another way in which we can create a primary amine is by taking sodium azide, reacting it with an alkyl halide, and then we can follow it by hydrogenation conditions to convert it into the amine. The third, in addition to the ones that we have discussed, because this is more like a review, when you have ammonia, you can actually do reductive amination, which was the last reaction we discussed in the previous video. And if you have sodium cyanoborohydride, then in situ you can have a reductive amination in which you have ammonia being introduced. In this case, we are utilizing an aldehyde, and then this is going to reduce to that primary amine. Primary amines then can be used to obtain secondary and tertiary amines. As you can see here, once you have that primary amine, you can do reductive amination to make that secondary amine. You can do another reductive amination to make that tertiary amine. Remember that reductive amination is where we utilize aldehyde or ketone, producing that amine that then can undergo with sodium cyanoborohydride that reductive amination. And if you need to make a quaternary ammonium ion, remember that alkylation of a tertiary amine can result in the formation of that. So, and again, between these last two slides, we are summarizing many of the reactions that were discussed in the previous video. The next thing that we are going to talk about is acylation of amines. So in acylation of amines, specifically, this is a reaction that was discussed when we were talking about the carboxylic acid derivatives. So I hope that you can recall that amines are converted into amides with the reactions with acid chlorides. So when we have an amine and we react it with an acid chloride, as you can see in the slide, then we are introducing that acyl group that was bonded to the acyl chloride onto the nitrogen atom. Now, when this occurs, understand that 2 moles of amine are going to be required. Acylation of an amine can be used as a protecting group. So let's consider now how to perform a monobromination of aniline. Okay, so let's say that if aniline is directly brominated, polybromination will be observed, because hopefully you can remember that from the aromatic chapter, we learned that that NH2 group, that amino group in the benzene, is an electron donating group. That means that it's going to activate that benzene, so it's going to be a really good nucleophile for electrophilic aromatic substitution. So if you have just aniline, then the bromination will occur at ortho and para positions. Now, in order to not have that polybromination, okay, or polyhalogenation of the system, the amine must first be protected as an amide. So what that means is that now this aniline molecule can be acylated, then having that acetyl group on the nitrogen, as you can see on the box, Once that molecule undergoes bromination, then as you can see, it's only going to brominate specifically at the para position. Okay. Now, after this, you could do an acidic or a basic workup, and that acyl group is going to fall off out of the nitrogen. The disadvantage of this synthesis is that the amide hydrolysis requires harsh condition. Now, aromatic amines also cannot undergo Friedel-Crafts directly. The amine reacts with the Lewis acid catalyst. So as you can see here, if we have aniline reacting under Friedel-Crafts conditions, one of the issues is that NH2 is going to react with aluminum chloride, and as you can see, that makes the ring be deactivated. So how can we achieve ring alkylation? Well, then you can first take the amine and acylate it. Once that happens, and as you can see, that nitrogen atom gets acylated, then the alkylation can happen. And at the last step of the reaction, you could use acid or you can use base. That is going to remove the acyl group from the nitrogen. And that's one way in which, instead of using just aniline, adding that acyl group to the nitrogen can allow these reactions to occur. Now, similar to alcohols, amines can serve as precursors for the synthesis of alkenes. We learned previously that an alcohol can undergo an elimination to make an alkene. And as you can see in the bottom part of the general reaction, we can see how this case an amine can also undergo elimination to form an alkene. So, how does this happen? Well, there's a reaction called the Hofmann Elimination. Excess methyl iodide can convert an amine into an ammonium salt. That is going to serve as a good leaving group. So, as you can see overall, let's say that you have specifically this primary amine, okay? You are going to add excess methyl iodide. Then, in the second step of the reaction, you can see how that silver oxide, water, and heat is going to specifically create the alkene that we see as the product. So overall, we are going to form a carbon-carbon double bond with the terminal carbon in this case. And this is a high percent yield. High percent yield meaning that this is the major product of the reaction. Now, this is the sequences of steps in order for Hofmann elimination to occur. So, in the beginning, when the excess methyl iodide is reacting with the amine, what we're doing is that we are alkylating the nitrogen, okay? And that's via SN2 process. After that, in the second step of the reaction, just go back to the slide, where we have the silver, the water, the heat. As you can see here, we are going to have specifically the formation of a hydroxide that then can pull the proton from the carbon that is at the outermost part of the molecule. In this case, it's going to be towards the right, and that is going to specifically create that nitrogen that has those three methyl groups be our leaving group. So that's where the E2 elimination is going to happen. So as you can see, Hofmann eliminations give the terminal alkene, meaning the least substituted alkene due to its regional selectivity. That's just a hallmark of this reaction. Now, if we try to rationalize why is it that the Hofmann elimination actually occurs, it overall comes from the idea that sterics in the anticoplanar conformation hinders the attack at the more substituted site. So if we look at the nitrogen atom that has the 3 methyl groups, and we look down between carbons 2 and 3, and we draw the Newman projection, as you can see here, overall, what we have here in between the nitrogen that has the 3 methyl groups and the tail end of carbon 3 is a gauche interaction. Okay, now if we look specifically between carbons 1 and 2, and we also draw the Newman projection, one the things that we can see is that specifically there's no gauche interaction in between the nitrogen that is completely methylated. So because if we have specifically no gauche interaction, which gauche interactions, even though they're staggered, they are not ideal just because those atoms are close proximity. That is the reason why we have the formation of that terminal, meaning that less substituted alkene under Hofmann elimination conditions. Now, amines can also be reacting with nitrous acid. Okay, nitrous acid is known to be unstable, and it has to be generated in situ in order to react with an amine. That means that you're going to already generate it in a flask, and then you're going to add the amine to it. Nitrous acid is going to lose water to form an active electrophile, which is called a nitrosonium ion. And as you can see here, the way that it is generated, this nitrosonium ion, is that you have sodium nitrite reacting with HCl. That is going to make our nitrous acid. Then our nitrous acid is going to be protonated to give the oxonium ion. Then the oxonium ion is going to lose water to give rise to that nitrosonium ion, which you can see that is the last molecules in the bottom of the slide. Here, I marked them with a check mark. This nitrosonium ion is actually extremely electrophilic and is very unstable. So it immediately reacts with an amine as soon as it forms. And here is just the resonance structure for the nitrosonium ion. So understand that if we have an amine and we have the conditions to make that nitrosonium ion, specifically the reaction of a secondary amine is going to yield an N-nitrosoamine, which you can see the product of the reaction in the general reaction that we see on top. The mechanism for this reaction specifically, as you can see, that sodium nitrite with HCl is going to make the nitrosonium ion. Then the amine is going to act as a nucleophile, and it's going, the lone pair that is in the nitrogen of the amine is going to attack the nitrogen in the nitrosonium ion. Then the water molecule that it is present, because most of the time you have aqueous acid in these systems, is going to deprotonate the hydrogen, putting the electrons back onto the nitrogen atom that came from the amine, and that's how we make the N-nitrosamine. Now, the reaction of a primary amine under the same conditions is going to make a diazonium ion. And this process is called diazotization. Now, as you can see here, what we have is that we're going to have an R group bonded to two nitrogens, and this is specifically is a diazonium salt. Let's now discuss the mechanism for making that diazonium salt. So, in this process, as you can see, the first step of the reaction is the mechanism of making that nitrosonium ion. Then the primary amine is going to attack similar to what we discussed a few moments ago for the secondary amine, which the lone pair on the nitrogen from the primary, in this case, the primary amine is going to attack the nitrogen in a nitrosonium ion. In the next step of the reaction, the water molecule is going to be deprotonating the product of the previous, or the molecule that was written as the product of the previous step. Then understand that what is going to happen is that there's going to be a proton transfer in which the oxygen atom that is double bonded to the nitrogen is going to receive a proton. Then there's going to be a sequential proton transfer. There's a series of them. But the second proton transfer is going to be removing the proton specifically that was present in the primary amine, okay, and it's going to form a double bond between the nitrogen atoms, followed by a third proton transfer in which the oxygen atom is protonated, forming an excellent leaving group. And as you can see here, in the last step of the reaction, we're going to be losing water in order to make that diazonium ion.